Fantastic.
Go ahead.
So today I'm going to give a brief overview on this very broad but also very expedient topic. So I'll first start an overview of how I see some of the exciting developments from the convergence of exponential technologies that you've been working with for the past 5 to 6 weeks. And I also give an introduction of some case studies. I will be looking at what technology is at the cusp of breaking out and available today. And I think that might help to inspire some questions or discussions later on. And we can also see like exactly in the process where you've been. So please share your experiences, please share your questions, and also let me know if you disagree with some of the points that I raised, because I'm sure that you will have a lot of this already in your facilities today. So you've seen my background last week, also Sarah just mentioned so briefly. My technical background is in robotics and machine learning, where I've spent the past 12 years in areas ranging from service robotics, so that's developing robots for our homes, such as here building an automated kitchen with the world's leading industrial robot manufacturer, which was more than 10 years ago, to working with NASA and humanoids for space exploration on, for instance, on Mars, to innovating high performance mobile manipulation solutions with shared autonomy for lights out manufacturing, as here on the very right. And this is a mouthful, but this is the very latest in terms of what you can bring to the factory floor. And that really allows you to say, you want to do things that previously weren't possible, really large scale manufacturing with high precision, with coordinated control. Those are things that until, let's say, 1 or 2 years ago wouldn't have been possible in the application, and now allow us to really break the boundaries of, say, work pieces or workspaces that you can work on by utilizing assets that you already have in place without re-engineering the process and investing into huge capex requirements. These days, I'm working more on the safe interaction of high-performance robots and humans when you deploy them in extreme environments, such as offshore facilities in oil and gas or in disaster zones. Previously, I've also spent significant time working on shared work cells for small and medium enterprises. So that's where you have your on-the-ground employees reconfigure your automation solutions. And that was more than 10 years ago, where you didn't have the cobots that were safe to work with people in the same workspace. So it was more about how do you facilitate that you don't have to build very complicated fences, and you can reconfigure based on smaller bed sizes and really make manufacturing more competitive on small bed sizes in high labor cost environments. For instance, if in this case in the West, when we've been talking about reshoring manufacturing. These days, however, we look more at something like a shared autonomy, where you try to push the autonomy on a system as high as possible, but you do not shy away from like unexpected scenarios where if there's something unexpected happen, it can delegate back to a human with a very high level decision making and guide the human in making the decision to resume the activity autonomously. And that really is an important concept that I'll touch on a few more times in this talk. But that is something where if you think you cannot automate something because there's too much variability or uncertainty in the process, don't be afraid of it. Something like shared autonomy or shared control can safely allow you to automate this and drop back to a human operator when absolutely necessary. And some of these examples can be in logistics, they can be in product handling, they can be in manufacturing, and we can get to that also in the discussion if you think there might be an application for it. Over the past year, so outside of technology, over the past decade, I've worked with lots of companies ranging from small startups to Fortune 500 companies in operations and innovation. Looking at optimizing, for instance, existing processes and architecting new product solution. And as I've touched upon on Friday, I've been working with EXO for the past 5 or 6 years, and the team, including all your esteemed coaches and advisors, for 5 years. And I'm very much looking forward to the discussion that we have later on. Anyways, let's get started. The first big question, of course, is what is Industry 4.0? There have been different definitions that included varying concepts. However, the term was first coined about 10 years ago in the high-tech strategy of the German government, and they unveiled it at the Hanover Fair, like the world's largest manufacturing fair at that year. But there's lots of abbreviations that are somehow related to it, and especially if you look at sharing happy social networks such as LinkedIn, you will frequently come across lots more abbreviations and new terms. But that are often just recombinations of the very same concepts into fancy new acronyms, which are then subsequently linked or related to Industry 4.0. And I'm sure you will have seen most of these. You will apply some of these in your day-to-day work, and also we've seen a lot of these in your initiatives in the last week. So I'm sure you're super familiar with them. However, what I'd like to do in today's talk is really bridge from these technologies via the business models into how they relate to the EXO methodology. and how these enable you to achieve, and especially how the robustness and the readiness that we see in these technologies now beyond these, there's an exponential trend, things are getting better, but we're having readiness today, how that allows you to integrate them to achieve efficiency and productivity, but also to aim for agility and resilience in your organization. And then seeing how you can integrate that with an EXO concept. Of course, a lot of these concepts you most likely will already have in your business today, because they build on existing concepts that have been prevalent for the past 20 years, most notably ERP, lean, and robotics. So there will be a lot that you already have on the ground, and that is good, because that means you can leverage these existing investments and developments, augment them, and drive new business value from them. And even though these have been around ERP, lean, and robotics, what really is the big difference in the last, say, 5 years is that now we're at a stage where software really makes the big difference, in the sense that we're at a stage where the hardware is cheap, it's commonly available, and we have a high level of integratability, and you can use software processes to iterate faster, drive value, and to really supercharge these existing machines and make them smart. And why Industry 4.0 is a big topic these days, of course, is since we've seen with COVID that companies that were already on a journey to digitizing with these Industry 4.0 technologies before COVID hit were a lot more agile to face the volatility that it was introduced to it, while the others were more susceptible to material shortage, steep drops in demand, of worker unavailability, to name three. But worse, they did not have the visibility, or they had very little visibility into the long-term effects that might come downstream in some time to come. However, when we do take a step back from these many buzzwords that I just showed a minute ago, is you can break Industry 4.0 essentially down to 4 core features when you apply them across the supply chain, across the value chain. The first one is surrounding connectivity, data, and compute, and this encompasses how we can instrument and connect systems to generate data and exchange the information, as well as how we transmit, store, and where we process this data. And this drives really the ability of systems, so that's your machines, your sensors, and your people, to connect and communicate with each other. So in an EXO context, these technologies are underlying the basic infrastructure that enable us to build interfaces, but they also touch upon the social technologies and the staff on demand that build this Internet of People, as well as a leveraged asset, since this allows us to utilize external investment on an OPEX rather than a CAPEX basis in the business, which really allows you to flip the return on investment equation quite a bit. The second key feature for Industry 4.0 is surrounding the human-machine interactions and information transparency. And the key here is that the interconnectivity from the first element allows operators to collect this immense amount of data and information from all points in your operation, and subsequently make decisions based on that comprehensive information. And this in turn enables the identification of the key areas that can benefit from improvement to increase your functionality. Part of this process is also to design systems that assist humans in decision-making and problem-solving, particularly surrounding difficult and unsafe tasks. And this is where, for instance, what I just mentioned with shared autonomy comes into play, where you can have this blended approach through a good human-machine interface. So putting these systems then into place enables you to bring in larger autonomy or decentralized decision-making that assist humans in their day-to-day decision-making and problem-solving steps, but it also makes the organization quicker to respond to emerging situations. And this can then result in systems where the decision-making is decentralized and fully empowered through the technology. And step by step, you can have the sliding bar where you move more and more to automation, the more data you gather and the more you can iterate on this process. And of course, in an EXO context, you would see a lot of these things in your interfaces, your dashboards, and your autonomy attributes. From here, it is very easy to see how the interconnectivity and the human-machine interfaces lead to the area where we try to extract either patterns in the data, or to enhance the automated decision-making, or to spot some trends in the data, which is all the varying elements of analytics and intelligence. And that can also allow us to supercharge other aspects of Industry 4.0, such as preventive maintenance or predictive maintenance, or also optimal utilization of machinery to stretch out the maintenance intervals that I'll touch upon in a second. And of course, in an EXO context, very evidently, those are your algorithms. And the final component, or the fourth element in what characterizes an Industry 4.0, is the fact that we're now having lots of novel processes that have reached maturity, or that are entering and upending existing processes. So that's your novel processes or your advanced engineering that get introduced into the value chain. And this is the stage where we can see that there's a clear overlap between Industry 4.0 and the fourth industrial revolution, as coined by the chairman of the World Economic Forum, Klaus Schwab, highlighted here. And this has been the predominant and more like holistic encompassing term that was used in, say, the past 5 to 6 years, because it also reflects the societal and the business model changes that come with this new change, or with Industry 4.0, or widespread application of it. And I argue that this is really important to take into account, because the technology changes and the novelties that Industry 4.0 bring will not bring you the step change improvements that you're looking for in returns, or that you may be able to potentially attain. And disruptors will fully utilize all of these effects to really harness the confluence of the exponential technologies. And in that context, of the fourth industrial revolution, you would always talk about the cyber physical systems, because that's a holistic picture of the hardware, the software, and the biology, which the people is. Looking back into history, and I'm aware you've seen that many times, I'll keep that a bit brief. The first industrial revolution really represented the mechanization, moving from hand production methods to machines. It was powered by the steam engine, and the first industry to really undergo it was textiles in the UK. But we've also seen this had a downstream societal change of a stronger middle class. We had the urbanization, which has lots and lots of second, third, fourth order effects that we all live through today. But it was also home to very horrible working conditions. The second industrial revolution is really about the changes to the production method and the introduction of advanced technology. And it started in the US right after the Civil Wars in the 1860s, and in Europe a little bit later. And historians often put 1871 as the year it started, because that was the year the unified German state was founded, and it had lots of changes for patent law, IP, and other implications. And this was really like the time frame of the latter half of the long 19th century that culminated at the eve of the First World War. And this time really was marked by the development of extensive railroad and telegraph networks, which enabled the faster transfer of people and ideas. And generally, it was a time of intellectual thought and invention, which has been thriving, because now you had this emergent patent system that was spreading in the UK, in Germany, in Europe in general. But you also had this time where this damper that was put on intellectual thinking of the very repressionalist states that emerged after the post-Napoleonic time, that really curbed what happened in innovation and what people did in like general intellectual thinking. And some of these key technologies that we had seen at that time that were instrumental were electrification, of course, oil, structural steel, and venture capital. And all of these were the confluent factors of the time. And it was also the beginning of these thinkings about what is the modern production line, the Taylorist, the Fordist system that really streamlined production and allowed mass manufacturing without personalization. I think that's an important key feature to take away here. So that was a time you had a large displacement of workers, huge societal changes, horrible working conditions, but first time you had mass affordability because of mass production without variability. And here we see the Model T, and of course everybody knows the quote from Henry Ford that you can have a car as long as in any color as long as it's black, and that really is one of the points that we can now got upended in the third revolution, but is now at a stage where we can loosen these restrictions more and more with the trends. And of course, the names that you find associated with the second industrial revolution are names that you're still familiar with today. So your Edisons, Tesla, Westinghouse, Carnegie, JP Morgan, Charles Schwab, and Henry Ford, and so on. So these names really are the emergence of the big household brands and multinationals that we see today. And then the third industrial revolution that we saw, the third revolution really was around digitizing, and that's the one that we've seen shape our lives, and that is the one that provides the current, say, state of the art in the late 20th century. The key feature here is, of course, computerization, the introduction of the internet and other communication technologies such as satellites early on before the internet was widespread. It has really allowed us to reduce stock keeping, to have just in time, to have a greater outsourcing, to have a better integration of the supply chain. And this is what we all know. And this what this really gave the end consumer was a lot more SKUs, a lot more complexity in the product, while still allowing to keep a cap on the cost. So this is what we see as the state of the art, even though a lot of organizations have been adopting bits and pieces of the Industry 4.0 over the past 15 years. But this digitization is really what is driving business today. But the key question is, what is different today? And what is different is that the nature in which organizations respond to adapt to the new opportunities presented, and also counter the risk of disruption here. So in the previous industrial revolutions, when the next generation came, you had to fully replace all your means of production and equipment. This was like a full, like it's starting from scratch, a full capital expenditure. What this means now is that you can selectively adopt bits and pieces of these technologies in your brownfield sites to streamline and make your processes more efficient. And this is great from an operational standpoint, but it also means it's leveling the playing field for any potential disruptors. But we would like to really focus on how you can augment and optimize your existing sites through these projects. And we've seen on Friday the initiatives you worked on that are perfect representations of what can be done to like bring in change selectively to augment the workspace. But what we see moreover in the manufacturing space is that this brings in this tectonic shift in three different places: in the business, the organization, and the product. And first, and that's especially for core teams, and we discussed it, for instance, on the smart textile initiatives that we saw on Friday. Can you move from products to something that's like a platform or an ecosystem? And one of the questions here, of course, is can you define these interfaces that allow you to exchange value for streams and that allow you to build an ecosystem of partners that create value based on capability that you open up to them? And in manufacturing and automotive, which is always at the very forefront of bringing these innovations, we've seen this in the platforms. Most of the cars in a certain size in a group, they always have the underlying same infrastructure. And there's a different hull that they, and different stuff they put on top, but the platform is the same. But we've also seen this in a more recent context where people take these platforms to achieve decentralized manufacturing or 3D printing. You have the same interface to access a manufacturing capability, but what is actually happening, what machine is doing the manufacturing, what process is handling any of the steps below is completely abstracted away in a platform. And we've also seen this in an ecosystem approach. Of course, if you look on mass processing, high performance processing, what NVIDIA achieved in the GPU space compared to their competitors such as AMD, their larger adoption in data centers and data science has really been driven that they were open to an ecosystem and very supportive of building this ecosystem and community early on, more than 13, 14 years ago. So I think the first time when I had contact with it, versus AMD, which like maybe started 5 years later, did not have the same investment, and it really showed in the adoption and domination of essentially the same space and capability. More recently, and related into the textile space, we've also seen this with companies introducing digital skin. So that is a flexible fabric that you can use to do force or contact sensing. And people in robotics, for instance, use it to figure out if you touch something or if you want to pick up something very delicate, say a fruit. If you don't want to squish the fruit with a robotic hand, you would use something like a digital skin to sense it. The problem with that is a technology change to be able to produce this flexible material, this very textile-like, but people have not figured out the right application or right distribution. So they open it up as an ecosystem, as something that fosters a community, and thereby they've been able to achieve a large adoption and a generation of new ideas and new innovation around this core technological change that they did not initially know how to commercialize. The second is more business model driven. It's really that we can move from CapEx to OpEx, and that's both helping you to realize processes because it reduces your requirements to invest. And you've seen it most likely in your office, the fact that you pay for printing on your copy machine by the number of pages printed rather than by buying the equipment. This was like the first one to innovate, but we've seen it more over in like fully integrated supply chains. So about 15 years ago, we saw integrated supply chains where you had, as part of one assembly line, there was a subset which it went through several buildings, where some of the buildings were suppliers, contractors, or OEMs that were doing value add steps on the same assembly line. Now we're seeing this much more integrated, where suppliers provide the equipment as part of your assembly line and then charge you for the manufacturing. So in automotive, it's something like rivet placing or adhesive application, where there's no investment in the capex of the machinery, but you pay by the pieces of work done. And you can also see it later in the examples. Robots that you bring in that we saw with some of the initiatives in the AGV initiatives last Friday, you can often pay for these by the goods processed rather than by the capex, and that really helps to like trial and do things. But what this also means is that we now see with a lot of these digital businesses that large amounts of their operational expenses are actually these these business services. For instance, a lot of the cloud providers spend up to 40% of their revenue in cloud infrastructure. So that's another thing, which means it can make your margins razor thin, but it also means that you might have a lot more competitors entering, because we have this shift where there's no large investment required anymore. You've seen that many times. And the third thing, and this is a direct consequence, is you can look at changing the business model. And ARM and Qualcomm are very known for like moving the expertise to an IP business model to prevent commoditization. But you can start from utilizing expertise rather than being stuck in a variable cost setting, for instance, with consulting services, and then figuring out a platform or product on top of that. And what that means on the bottom line, if we look at this very, very common Venn diagram, this age-old paradigm that you can only pick 2 out of 3 when you look at price, quality, or customization, this is really upended. And the point is, it might not always be, especially if you take the 4th point, turnaround time, into account. But the point is, I want you to break down the barrier of seeing that these 2 things don't go with each other, and ask, what if we can make this work, and what needs to change to have all of these things at the same time? And how do these technologies that we're going to go through right now, how do these help us to maybe break down some of these conflicts that you would traditionally see in implementation? Under this long backdrop, sorry.
Wolfgang, let's just pause for a minute. Let's do a temperature check on the audience. Sprinters, any questions? How's it going?
I think we are good to go, Zahira. We can continue session.
All good?
Okay, yeah, thanks so much. Was good stopping now. Okay, under this entire backdrop of the framing, what this brings is, I will focus now on concrete examples of recent technology breakthroughs and what I think is at a mature stage right now in the different technology categories that might be a bit of inspiration. And I'm certain that after the 5 weeks that you spent in the sprint, you will be very familiar with the opportunity for exponential thinking that will lie at the intersection or confluence of these trends, or that these examples might inspire. So I hope that this provides some breadcrumbs of innovation or technology that can stimulate a discussion later on. I'll briefly break them down into 3 categories. The first one is really just like minimal improvements to drive efficiency and productivity in existing facilities. The second is looking at adding agility and resilience to your existing process, or what people have done in the field. And the third one is really, how can you push boundaries and add value? To start with the first one, driving efficiency and productivity, the most commonly named one is, of course, distributed sensors, or the industrial Internet of Things, where you have lots of inexpensive sensors that capture all the data on your processes, and you're using them. Everybody's using them. But the point I'd like to drive down here is, these are really cheap now because of the commoditized and well-done supply chains that we see for smartphones. But the second part is, on the back of this, there's been really a drive to develop open platforms, and particularly open hardware that allow you to prototype really easily, including with on-device computation, edge computation, so you don't necessarily need the cloud. You can be less restricted in your deployment, and you can integrate it in your existing infrastructure and with the cloud. So the point here is this open platform, open hardware approach really allows you to digitize equipment that you might have that currently is not able to be integrated, and really get them into your processes. And these are super inexpensive. And together with the algorithms, you will be able to integrate, I'd say, almost any kind of equipment. And that is really a step change. However, one thing to look for, especially if you look at the more consumer side of things, but also with the industrial side of things, is both the cybersecurity implications. We're seeing lots and lots of shutdown due to improper implementation. So just this morning, there was an announcement that about 20% of the US beef producing capacity was taken offline by a cyber attack. We had it maybe 2 weeks ago that on the East Coast, they took out the pipelines in the US. So there was gas price hikes. So really be careful when you look at these things about what are the cybersecurity implications, and also what are the technical support timeframes. A lot of these equipments, they will not last as long as the equipment that you already have in place. So that is really currently a challenge. So be careful about that when you implement it. The second one, and I'm certain you have it in many different places, and you have lots of people here that are familiar with. If you want to automate digital computerized systems, you can use RPA, and these are the key vendors. For instance, if you want to automatically extract information from an email, copy it into ERP or your Salesforce and so on, you can already automate that directly, and I'm sure you've been using it. The second one, and I think that is helpful for when you're going through the prototyping phase now in this stage of the sprint. If you find a cool API online, say for machine vision that you want to use or something else, and you want to build a quick prototype, you can use these more programmatic drag and drop services that allow you to combine APIs of, if a service has an API, you can combine them with these tools, versus the first step, the RPA, is more, if you have something that's like free form, a process that usually a data entry person would do, you can automate them. And both of these things might help you in the prototyping stage, for instance, to get a bit more automation into processes that usually would be custom. The second, and we've seen that and discussed it in some of the feedback last week, was VR, AR, and wearables. They've been hugely deployed in many areas, and I think some of the ones I mentioned was the hands-free augmentation we saw on, for instance, in logistics, where companies use AR classes to automatically do the barcode scanning. So there's no more need for variables. So we're jumping the step. You don't need a variable, which has been probably in the field for 20 years. You can do it directly with scanning, with computer vision based on AR classes that people carry. But at the same time, that allows you to have information in there, for instance, how you should stack boxes so that they're more stable and they don't fall over when they're transported with a forklift. And we've seen the same thing in maintenance, where you allow people to have both hands free to be more flexible and deployed. And then, of course, we discussed onboarding and training with VR last week, and the ability to reduce personnel on site. But the point I'd like to make here, beyond VR or AR and what it can bring to your supply chain, is that this is a step change in two respects. And the first one is I'd like to encourage you to rethink user interfaces in the sense that you can now tailor them to workflows to reduce error. And this is a really clear benefit that can drive tangible outcomes, right? So on the left-hand side, you can see the space shuttle user interface, lots of buttons, very expensive to build, very expensive to change if you have a process, and very complicated to memorize where everything is and what stage of the flight. And on the right-hand side, you see the user interface of the SpaceX shuttle capsule, and probably many of you have watched the launch this year. But the point here really is twofold. The first one is everything is now digitized, it's easier, and it can be customized to the stage of process that you're in. And this is similar to if you think about the Uber app, right? There are hundreds of different user stories and user interfaces that are in the app. And you will only be seeing very, very few of them based on your location. So that's your city, based on your payment workflow, whether you're a business customer or a industrial customer. So you only see a subset. It's targeted to what you're exactly doing. And I think that's part of the takeaway I'd like you to take here for processes when you design interfaces. And the second point here is dematerialization. The interface on the right is completely web browser technology based. And that means you now suddenly have a greatly increased talent pool that you can tap into to realize these processes when you bring them in. And finding a web developer is super easy. Finding an embedded systems engineer, not so much. And similarly, of course, very related, you can now find these no-code platforms, and for your prototyping now that might be super relevant, where you can drag and drop things and build user interfaces to experiment very quickly with, and you can get them with vendor guarantees, SLAs, whatever you need from, say, AWS, Microsoft, Google. These are now from big tech readily available today. Looking more at what we can do with sensors, I'd like to talk a little bit about predictive and preventive maintenance. And of course, that's where you try to use those sensors to predict when a component will wear out. And that allows you to plan your maintenance more flexibly. So you can cope with a surge in demand. You can, based on your sensor data, determine that you might be able to run equipment for longer, postpone that maintenance interval. Or for instance, you can already reduce the downtime by sourcing in time. And that is especially important when you want to reduce stock keeping on spare parts of machinery that have very long lead time. So for instance, in offshore oil and gas, if something wears out on an offshore platform, you need to book a ship, you need to get it to the ship in time. So there's a lot of logistics involved. So they're very heavily adopting predictive maintenance to get the right parts to the location to avoid downtime on these platforms. And especially when you have very challenging logistics, it's more and more important. But the other applications were the same idea of using these sensors to first capture data and then maybe later use it to learn a model and so apply machine learning to get better utilization out of equipment. And one of these examples is if you want to reduce the energy consumption throughout the lifetime, because energy consumption is very heavily dependent on the wear and tear. So between your maintenance cycles, you will see a fluctuation in the output that you get out of a machinery. And this can be very common if you think about a compressor, a large motor that you might have on site. These things, they have very heavily different energy consumptions depending on their maintenance. And that can also be a flip side. You can, if you learn a good model, you can change how the control method works on those machines to reduce the energy consumption to still achieve the same output. And that can really have quite a bit of impact on your energy use today. That might be a leading factor in some of the product lines. And we've seen that with some customers where that has been a significant, if they reduce energy by 10%. But we've also seen it that smart algorithms now can use existing machinery, say robots, to have exactly the same motion on the robot, and just by slightly tweaking how the robot works, you can reduce energy consumption 30% on those assembly lines. And for instance, Volkswagen has done that on their assembly lines, and like 30% on their energy bill is quite a lot compared to, especially if you have a fully automated supply system. The next big step is if you look at all the different areas of AI. The point that I'd like to make here is that while you've seen a lot of these around, a lot of these are now reaching maturity where you can drag and drop them in interfaces with your own data without having to sit down and set up a specific system, have a computer scientist, a data scientist deal with it. You can do this in the cloud, upload your data set and try different models out, drag and drop without too much like coding requirement or technology requirement. And once you found a model and fine-tuned it to your satisfaction, you have a one-click way to deploy it as an API that you can then integrate back in your product, similar to the drag and drop systems I showed earlier for API integration, or in your existing development. And of course, the more data you have and the easier you can label, the easier you can get predictions. But we've also now seen customers and large companies employ other kinds of machine learning. For instance, Google very widely is using reinforcement learning to cut down on their air conditioning energy use and requirements in data centers, and they can save 20 to 30% on the energy there by using advanced machine learning models to change the behavior. The second point.
We have a question. We have a question. Please explain how we can use this in compressor for energy savings.
Okay. So for compressor energy savings, for instance, between maintenance cycles on very large compressors, one example that I've recently looked at is in gas. When you compress gas, you will see that the metal parts they have corrosion over time. They wear out, and you get wear and tear and slack in the bearings, for instance. And usually you will just like run to achieve a certain pressure or a certain setting. But if you instrument, you can learn what the input, so that's usually a PWM if you have a three-phase system, how your input system affects the output, and you can change the input, for instance, the input phasing to get it to achieve your output. And similarly, since this is a very large, and this might be super technical, since it's a very large inertial system that some of these motors drive, you can predict the speed and spinning. So instead of ramping up all the way in a traditional PID control setting, ramping up all the way to your region and maybe breaking down to not overshoot, you can predict the output system evolution based on the input. So that's most likely your PWM signal on many of these, or your phase changes. And based on that, you can make sure that you don't have too much input to achieve the required output. The second point is you can much more accurately model what's inside. So traditionally, these systems will be driven by a PID controller to achieve whatever the output is with a very simplified model of the system. You can measure over time how the friction inside the system changes. And friction is usually considered of two. You have your viscous and your static friction. And these things change with corrosion quite a bit. And also with like shock effects when you have a bearing wearing out, and that has an impact on the energy use that you require to achieve the certain speed. If you can measure those, you can compensate for them in your control system. And that means your controller gets more complicated because your model is more complicated. But this is not a problem anymore with modern compute, even on a normal computer. So the point is you need to capture your inputs and your outputs as accurately as possible. and then you can learn like the transfer function mapping and build a predictive controller on it. I'm not sure if that was way too technical now, but that's the process. And we've seen in, for instance, in chemical engineering plants as well, where you can then define linear sub-regiments. And if you've done operations research or operations management, you've seen that probably with linear programming. There's more complex ways than you can do that than just linear programming, to have these sub-regions in which you would apply a certain control law, or if you have a good model, you can do everything on a model predictive control fashion.
Right. Thank you. Girish, does that answer your question?
Yeah, somewhat. Thank you.
All right. Okay. Wolfgang, another question that I had for you. How would you differentiate between edge computing and quantum computing?
So edge computing means anything. So if you have the cloud that is somewhere big in like a data center, the edge is on your device. So edge computing would be if you run a neural network directly on your smartphone, that is edge computing. If you run it directly on a very small computing node inside the machinery, that is edge computing. Those are still the same processors that you have in your normal laptop, in your smartphone, somewhere else. Quantum computing is this paradigm shift where you have a quantum. So instead of have a binary state 0 and 1, you have a quantum state, and that changes everything from the way we write software to the way these systems are. And while there's a lot of breakthrough in quantum computing today, it is not a technology that is mature that you can buy one and put them in a factory today. So it's a much more research subject today. And the key point is also that if I say an algorithm today that works perfectly on a normal computing system, it may not mean that it will work on a quantum computing system. So yes, edge computing, it runs on your end user devices or on your local computer rather than in the cloud on a big server.
Right.
So one flip side of that, and this is important, why edge computing is a big deal these days, because you would say, well, I have less compute power on my computer or my smartphone than I have in the cloud, is you have less data transmission. You can respond faster. So if for instance, if you have poor network communication or you have a low power requirement, say you have a sensor somewhere where you cannot put a power supply to, you would need to consider something like edge computing to reduce the requirement to transmit data back to a data center. So that's an option where you would go for edge computing. The other option is, if you need a faster response, then the round trip time to a server and back takes. So a lot of in real-time control, you will always have an edge computing solution.
Right. Thank you. One last question before you proceed. Could you give me a layman's understanding of reinforcement learning with an example? Yeah, absolutely. So supervised learning is you have your input and you define and you give and label the output. So you can explicitly say, I don't know, this is a picture, this is an apple, and you have the mapping and somebody sits there and says this is an apple. That means for scaling your data set, somebody needs to, an expert in your domain, needs to sit there and label it. Unsupervised learning is looking for patterns in the data. So like you group objects by similarity, for instance. That's unsupervised learning. Reinforcement learning is something where you have an agent that works in an environment and gets rewards. It's similar to a child learning to walk. When it falls down, the pain of falling down is the reward in that sense, and like not falling down is the reward. And it then needs to figure out. So you're not telling the child you need to take that step exactly, you need to move this muscle to do this. It's more you learn through the higher level response you can give. So you would use it in settings where it's easy for you to have a very high level semantic feedback, even over a longer time frame. Say you want to simulate a system running over, like a plant running over an hour, and you want to, at the end of the hour, you want to say productivity improved or decreased. But you don't want to be sitting there exactly and saying you turned this knob at that time and this is exactly wrong or right. In a reinforcement learning setting, it means the computer needs to be able to have a lot more experiences than with supervised learning. So we're talking millions to billions to tens of billions of experiences that the computer needs to collect. But with simulations, or Industry 4.0 speak, digital twins, this is not a problem to get these. So it's more you have this game of interacting and then getting a reward much later, whether it was good or bad, on a much more higher level meaning than exactly saying you turned this button by a little bit too much at that very time, as in other areas of machine learning. Thank you. Nicely explained. Thank you.
Great.
Let's continue.
Thank you. I think one of the examples where machine learning is really widely used in manufacturing now is automatic quality control. And I think what I just said, with you have tools where you can do it yourself, you can literally do this. So you can build your own data sets, and there's lots of tools where you upload images, for instance, and then you label it, or you have you have assisted labeling that suggests labels, and you just correct the labels. And that allows you to build data sets to then use supervised learning to do automatic quality control. And that's super widely used, with the difference that when it was used 20 years ago, it wasn't machine learning based, and it was a custom setup for every product. Now you can build these systems yourself and deploy them in your lines. And one of the companies, for instance, that does it is Landing AI. They focus on semiconductors and other areas of manufacturing, which allow them to catch defects much quicker than with human intervention. But you can also self-provision them, as I just said, with these platforms that you can buy. And you can also use computer vision for other processes outside of quality control, with models you can deploy yourself, thinking like detecting anomalies in your process or instrumenting lots more machinery visually than you usually would. If you do inspection at many more stages than previously, so you can catch defects much sooner. But you can also think about in a COVID setting or in a machine setting, you can automatically measure the safety distance between people. So you detect where the people are, you measure the distance in between, and you can have alerts, if, for instance, if their people are getting too close in a COVID scenario, or if people are doing things that are unsafe near machinery. So one of the examples is if you have heavy loading equipment, you have cranes, and your risk assessments tell your people not to walk underneath a heavy load or crane or forklift, but people still do it. Many times you will not be able to catch those things. You now can think about computer vision systems that automatically like sound warnings if somebody does an unsafe behavior that might lead to consequences down the road. And this is, I think, where a lot of these processes and a lot of the self-provisioning that you can do yourself really is breaking out, and where you can drive an impact in areas that previously wouldn't have been attainable. The other area, and I think now I begin lots of examples in robotics, is material handling and AGVs. And you've seen that. We've seen an initiative on that last week. Of course, it started in automotive, as many things do. The point here from an industry perspective is you can handle workforce shortages, you have more flexibility, and you can free up the labor for higher value tasks. But robots aren't great at fine-grained handling. And this is really where you can have this interplay between a robot doing a low-value task to keep people that are really good at skills, for instance, or fine-grained manipulation, to keep them at their most effective. And this is super commonplace. The difference between what you see here, for instance, and what we see now is that there's literally dozens of manufacturers that have similar solutions that you can pick from. So it is really a buyer's market, and that's good for anybody trying to adopt it. But the other point is that this advances in software that we're seeing, making these systems smarter and safer around people. And they also allow us to get other benefits. So if we, for instance, look at a palletizing solution, we're now at a stage where robots cannot automatically detect what's on a pallet and where it belongs and how to place it, but we can also have optimized driving profiles. So if you might have an issue where a driver was driving too fast on the forklift or too slow and accelerating, decelerating, things were falling off a pallet. These systems optimize both for machine wear, so they reduce the wear of your forklifts and of your equipment by optimizing how they move, and at the same time they reduce, say, the errors in packing or the defects from driving. And this doesn't have to be limited to palletized goods, for instance. The second aspect, which is now really just breaking out the last 2-3 years, is, or literally as we speak, with suppliers entering the market every week, is where you have an arm on these vehicles. So if you need to pick something up from a shelf, you can automatically place it. So where you previously, in the previous solutions, had workers prepare products onto a system, hand it over to a robot, the robot does it and then hands it over to a person again. You can now do a lot of these manual handling tasks of non-packaged goods directly with robots. And that is advancing, but that's also commonly used, for instance, in things like online shoe stores, in like everything, including return and replacement. All of these things are fully automated in warehouses. There's no more people like involved in this process of the logistics. And both of these solutions that you see here, they adapt intelligently to the layout, to people walking in the scene, and you can bring them into sites without having to reorganize. And that allows you to have a lot more SKUs than previously. The second area, and that's of course a big topic in the last 10 years, is these cobots. These are robots that are safe to operate around people without having cages. And The second, so that makes them easier and cheaper to get. So these are usually between 20 and 50K. There are hundreds of models, and you can literally pick based on your weight requirement and your reachability and all these other factors, and you will find dozens of solutions for every application you're looking for. So that's great. They're safe, they're cheap. You don't have to change your infrastructure around them. And you can also get them on like push carts or stuff that you can push them around to the place they need to be. So you can very rapidly reconfigure your workflow based on like changes in batches or changes in requirements. The second innovation, and this is mostly a software thing these days, is that they're easier to set up. So you can have kinesthetic teaching. You don't need training. You don't need to have a vendor come in to reprogram them for you. Your shop floor people can redeploy them as they see fit. But the limitation at this moment is still they have very limited motion planning and collision avoidance. So once you tell them what to do, they'll do it. They're safe. They're not going to crash into things, but they're not going to like change a little bit based on what things are. But this is changing as we speak, since no-code robotic comes, where you can have a lot more of these advanced algorithms, take exactly the same hardware. If you already have them, you can just get the software. And that really allow you to have more versatile adaptation to, say, variation that you might have in your shop floor. And cobots, of course, they've been really widely used. The arms are the most famous one, but in logistics that we just spoke about a second ago, we've also seen them. So on the left-hand side, you see things that require full greenfield sites or full adaptation. So the top one is the Amazon warehouses, where robots move the shelves to the people. That is a full change of your existing layout. The bottom one is Ocado. That's a UK grocery supplier. They re-engineered the entire warehouse for robots only. So there's no way that the people can come in because they drive on top of the shelf. So these things are expensive. They require greenfield investment. But on the right-hand side, you see another type of cobot where you can see this interaction directly. It drives around, it interacts with the person, they scan a receipt, and then on it goes and goes on its mission. So this is really just the material handling, the doing stuff repeatedly after you teach them kind of robotics. The other kind that is really interesting is where these algorithms, and in this case also reinforcement learning, comes in, is doing things that were previously really complicated. Because if you want to automate, you want to make sure you have 99 point lots of nines % reliability. You cannot stop the entire assembly line because the robot drops one parcel when packaging or something like that. So that would be really on a net basis a disimprovement, even when bringing in a system. So always think about, is the reliability good enough for you to adopt this technology today? And the breakthrough in the last, I'd say 18 months are these two systems here, which really achieve like close to 100% pickability in bin picking and automation. And they're super widely deployed these days. And again, they're retrofit solutions that you can bring onto existing lines that you have that are mostly software based, that then will allow you to have like really reliable bin picking of many different screws and products. If they're soft, if they're hard, they can handle all of these and respond to failures in the system. And one of these examples, for instance, in online pharmacies, shows that they can operate warehouses with 10 to 15 times fewer employees than competitors that also use robots but do not use robotic bin picking. Of course, the other option is logistics on a bigger scale is when you think about unloading and stacking of large scale systems and or large boxes, containers, delivery vehicles. And that is a tough task, but we're now also seeing fully automated solutions entering here. And the point is, we're now moving from a stage where these were restricted to environments that were fully constrained to regular boxes, regular shipment sizes in containers, very well organized, to stages where the software empowers them to work in really complex scenarios where you have the mess of a normal workplace where boxes are all over the place. And these systems, they're again retrofit. You can get them into like the workspace, and these systems, and these two, they're not yet ready on the market, but they're going to be shipping, and I think end of the year or next year. The second big aspect is exoskeletons, and you might have seen the one on the left hand side, which is something that empowers. It's guided by the human. The human is the intelligence, but it empowers them to do a task that usually 3 people would do with 1 person by using force around it. And it looks a bit like a sci-fi movie. It looks rather impractical. It still is quite experimental, and of course this is more like a military or heavy industry application. But the point I'd like to make is, while you might see these in popular science, what really is on the factory floor for almost 20 years now is more like passive exoskeletons that augment workers. And the example here is something from again, car, automotive, that has been on the factory floor for about 10 years. That is a passive system that takes the stress and strain out. So it prevents repetitive strain injuries and it reduces injuries in the workplace, but still uses the people, but still improves productivity. And similarly, we've seen NASA, for instance, has developed a glove system. So it's an exoskeleton on the hand that when you do grasping tasks that require a lot of grasping force that would lead to strain injuries, it will lock automatically with algorithms around your grip, enhance your strength, and this way reduce RSI in heavy duty applications quite significantly. That has been used for 20 years now in product. So there is a lot out there that can augment and also reduce your risk and reduce your injury, and that really has a bottom line impact just because you might be able to drop down in your insurance or your risk rating. So there might be an auxiliary benefit that is not directly attributable to a cost saving in the direct area. The other point where we look at the confluence of technologies is really when you look at, say you take the robots, you take these innovations that we see in haptics, and this is things that have been used in motion pictures for 30 years, I'd say. And you combine these with the ability that we're now entering this phase of better connectivity, especially lower latency. So the point I'd like to make is it's a commercial that aired this week, but it is actually not a fake commercial. This is not CGI. This is actually realistic, the state of the art in robotics you can do now. With this high ability to sense and transmit with low latency, you can have in applications where you cannot automate things because there might be irregularity. You need the smartness of the smarts that the human provides to automate something. You can use remote operation and remote supervision of people that provide the smarts with equipment that is in situ where you need it. And one of these applications that is super famous is if you think about forklift operation. That's an example from an actual company. The forklifts they run autonomously most of the time on the factory floor, but there are certain places where the people engages the system with a remote teleoperation setting, as you can see on the left-hand side, and does like that fine-grained manipulation as if they were sitting on the handling equipment, but they're doing it remotely. And that's exactly the same process people are using these days in self-driving cars, that they're using, especially in trucks. Trucks can be like automated on highways, and then on the ranging on facility side, you would use the remote control equipment. And in areas like mining in Australia, this has been the go-to thing for about 20 years. So the point here really is, don't be afraid. If you think something cannot be fully automated, you might find a blend, or you might be able to use the same technologies to find something where you can get a human back in the loop and use the intuition that only a human can provide. And the point here is also with this kind of remote teleoperation, in these situations and with shared autonomy, a human might be able to operate 10 or 20 of these machines at the same time. So your scalability is no longer constrained by skilled labor in these applications. The second aspect, yep.
Let's just pause and take 2 questions which have popped up in the chat. So I would invite Nikunj to come off mute and raise your question, please.
Hi, Merkt. So am I audible?
You are.
So my question is that what should the existing employees do to accelerate the change that we are bringing in Industry 4.0? So what skills do they need to have? What do they need to learn in order to be a part of the change rather than being just a witness to the change? So we are including some gadgets like sensors and like you told earlier about the preventive maintenance. We are into AI, but we are just purchasing those sensors and we are reading the data that they provide. But we are not actually being a part of the change. We are just witnessing what is changing in the world.
That's an excellent question, and it's super on the money. I think the point is, what skills do you need in the first stage? The first one is looking at the processes, mapping out your processes explicitly, and capturing the knowledge of your most skilled people that might not be written down usually, right? You might have a skilled machine operator that knows exactly, like they look at the machine, they can tell exactly that in 4 weeks this thing is going to break down. And this is because of their experience, 40 years or something in this area. Try to capture all of that, try to map out the process, and try to look for steps that you can innovate, that you can optimize, innovate, and automate. Find your bottleneck. So that's the traditional advice. But then also ask if you can skip a couple steps. for the so that's why I think there's not too much skill needed to get started, because through your observation and through capturing what you already know, or what collectively the people in your organization already know from the experience, you will be able to find exactly what to measure and what to witness. The second point, you're only witnessing, you're not yet taking action. I think witnessing is the first stage. Take the expertise, what you need to capture as much as possible. And a lot of this information at the moment will be that information. You will capture it in a database somewhere. People probably won't take immediate action on it. That is because initially a lot of this data will not have business value, because you cannot assign effects to it, right? So the point is, if you capture all this data about a machine that's perfectly healthy now, for the next 2 years, you're probably just witnessing, but the moment it breaks down, you can assign this event that there was a breakdown, and you might look back and look into like explainability in the data. Was there a point where we could have known it before? Without instrumenting today and capturing all this data today, you might not be able to exactly figure out how to prevent it in the future. And I think that's why in many cases, when you get started, you're absolutely right. You're probably just going to be witnessing for quite some time. So unless there is a transferable solution, or unless you can have a strong enough hypothesis, for instance, with the ventilation, that as one example, or with examples like in natural gas with the compressors there, if you can translate that to your compressors, those same processes and same applications, you can directly utilize the data and make use of it. But initially, you're most likely going to be witnessing, and then you can start looking at finding patterns in the data if that's something of interest. But I think moreover, it's more you're labeling it as you go and as you experience events. So for maintenance, it's very rare when you actually have a breakdown, or when you have a maintenance and you can assign like a wear factor that you see then, so you can get a little bit of meaning into the data. In other cases, you might be able to get results much quicker, right? So if you want to do quality assurance, you would start capturing the process next to the people that are already doing the job. You will have those experts label the data that you're capturing and the sensors that you're capturing. And then you're going to build these models, whether that's yourself, whether that's somebody else that does data science, or whether that's like through an external resource. And then you're going to deploy it at the same time. So then the system that is deployed will witness the work of the experts that you have in the field. And then once you're comfortable that these steps match what the expert would, when the system matches what the expert would do, you would flip the script and have the expert monitor the system while the system takes charge and takes the decision. And once you're then happy, the fourth step would be you take the expert out of the place and put them into a different task in a different location. So that would usually be the 4-step process. But to very brief to your initial question, in many cases you will only be witnessing, but you will not be able to attribute effects later until you actually have an event that was caused from the data. But it will still give you value when you can look into the explainability and look back and say, well, we could have noticed it 5 months ago when there was a change. So that is that aspect. The other aspect is if it is a very periodic data, you might already be able to capture some of these with anomaly detection. This is looking at if something in the signal changes. So one example, if you have a drill bit that's always drilling a hole, you can measure the current that the machine takes, and there will be fluctuations in the wattage. And if it always drills the same piece, you would expect that the pattern of the fluctuation of the energy it takes to do the drilling, it will change with the depth. And so it will be a very periodic, very repeatable signal. If you suddenly see a big change in the signal, that will either have one of two consequences, right? Your drill bit stalled in the workpiece, there has been a breakdown, or you see a wearing down of the tool. And those things you can detect with like time series anomaly detection. This is something where you could use the data right away. So yes, either it's witnessing until you can have attributability, or you use anomaly detection if it's something where you can expect very continuous, very predictable data early on.
Thank you. Nikunj, is that, does it answer your question?
Yes, ma'am, to a large extent. And it also brings more questions in my mind. So I'll hold that for a while. I'll shoot it once. Like,
you can tell us what's your question.
While Mark was talking about the data, so we have tremendous amount of data. We have the ERP system, we are in line with it. But when we talk about automating the processes, the data that we already have will take us to a preparation stage only, but it will not equip us for the change itself. So I cannot onboard the automation until I have the fresh and live data. The data that I already have can only take me to the barrier itself, to the front line itself, but it cannot help me on embark the automation. So that is what is going inside the mind, that how we can transform that into a fresh and live data that can actually help us embark the automation stage.
Yeah, very important. I think I would take it from this perspective. One, it's an asset that you already have this data. Whether that's an asset that you can utilize it by figuring out the right machine learning model to create value, or looking retrospectively to create value, or finding something you didn't capture at the time. That is one opportunity. But the other way I would see it is when you start from mapping out the processes and looking at all the different opportunities and all the different possibilities of bringing in innovation or initiatives, the data that you already have can provide the evidence what to prioritize, or where you could see value for that. And of course, I'm not privy to all the data silos that you have and what the granularity of the data is and what exactly it represents. And that's something you need to map out. I think as a good exercise, always look at all the things you have and if it can be of any use. And even if it doesn't allow you to build this perfect model that can, say, reduce the energy consumption tomorrow, it might give you the evidence that instead of looking at this initiative, you should prioritize the other initiative based on your historic data. So I would rather look at it from this way. And the second point is when you look at you have your process mapped out and you figured out where you want to potentially optimize something because you from experience know that it's a bottleneck, you can ask yourself, what would we need to capture to make a decision or to bring in a solution? And then look back if you already have it, or if you need to add extra like sensors in that sense to capture it. And that's how I would see it. I don't think it's a problem what you're describing. I think it's a tremendous asset and opportunity, because you can use it to make justification or to make prioritization, or perhaps even it's already ready in a state where you can say, look, we already did the instrumentation, we have 2 years of data in this area. It's really easy and inexpensive to roll out this initiative because we did all of that investment as part of something else a couple of years ago.
Right. Next question from Kunal. Any examples of applying 4.0 in the textile industry?
I think a lot of integrated supply chain. So if you look at fast fashion, it got a lot of bad rap, but there's, I would say, generations of fast fashion that came, right? So you first had the quicker turnaround. That was still often in many cases this traditional supply chain where you went from the retailer, the distributor, to the importer or the coordinator importer, which most likely was somebody in Hong Kong that then coordinated the factory somewhere else. A lot of that is ERP driven with 4.0. And to sense a lot of that really comes into play if you look at some of the, let's say, second generation fast fashion brands, the ones that moved from 3-week turnaround to actually later. So one of the examples there is rather than having this traditional, you weave, you dye, you produce the like t-shirt or whatever the end item is, and then you ship. There often is a change in process where they say we manufacture the item first and we dye later. And this is driven as part of a result of like a sensorification and a faster, more agile, fully integrated supply chain in Industry 4.0 setting where the first products hit the shelves or when they have more updated customer research, they change what the product is while it already is in manufacturing in the supply chain. And I think that is a good example. And when you want to take that to the next step, you would reduce your batch sizes, right? If you have Industry 4.0 and you can automatically transport your goods to the right places and you reduce the changeover time, or you become more flexible. And I'll show you one example of something called a line to matrix manufacturing paradigm. If you get to that stage, for instance, you can reduce your batch sizes so low that it's almost a customized equipment still at the price of mass manufactured goods, and you can do a lot of these customization steps later on. So yeah, dyeing after sewing, I think that's one example. And then a lot of it, that the fact that we're now at a stage where a lot of these fashion brands in fast fashion, they go like 3 weeks from first draft to on the shelf in stores. But a lot of that for them meant also like completely changing the supply chain of we're going from Far East Asia via Hong Kong to Europe to either owning or to doing a lot more high value manufacturing steps closer, decentralized to the store. So if you look in Europe, some of these brands, they own their own manufacturing lines distributed in Europe, much closer to the end consumer, to completely eliminate the sea shipping as one example, and like cut those weeks out of the process. So I think those are the examples where that goes into textile. And then I realize in textile there's a lot of still hand labor, manual labor involved, just because fabrics, they're super flexible. It's not something a robot or a machine can very easily deal with on especially if it looks at fine-grained, like more complicated items. But people are completely rethinking about how we do these things. So you cannot have a robot pick up and sew like a fabric that's like flopping about. But we're seeing a lot of innovation and research in handling soft tissue, soft cloth with robots, but that is research stages. But what is more looking to go into the factory is what if you change the state of the textile before you do the manufacturing steps on it. So that's stuff like freezing or using chemicals to make the textiles hard and rigid. Then you do the cutting and the sewing with a machine, and then you use another chemical to like make it again a fabric and into like a cloth state. So this is really like where we're moving from. We're just bringing a 4.0 something sensorification, integration of supply chain into you're really questioning the steps in the process and whether you can completely change them.
Excellent. Let's move ahead. We've got about 6 minutes more, so let's.
Okay,
plan.
I'll speed it up. Thank you. Yeah, one concept in agility and rigidity. You've probably seen it if you have a lot of ERP data. If you have, you can create like a supply chain nerve center or control tower. Then whether that is like a human that gets the decision, that needs to have the capability and the autonomy to make the decision. There shouldn't be like large chains where you need to escalate to get the approval. So that should usually be very with direct access to high-level decision makers. But that really allows you also to then have a way to like look at all these informations that you aggregate and the insights that you extract, say with algorithms, and present in a dashboard. And one of the examples that I saw in China from Huawei is this. This is the supply chain nerve center of Huawei. This is a massive, of course, centralized facility where every shipment, the status of every equipment that they ever shipped is tracked, and every anomaly gets directly flagged up. So if there's you can see there's some maps, of course you see the status, you see the health status. Like this is like the biggest dashboard you can imagine, and it automatically algorithms flag up what is important and change what the direct respondents in this control center that you can see in the tables here do. So for instance, if there's an adverse weather event that might affect the shipment, that might affect telecommunications infrastructure in one part of the world, it will get flagged up automatically and will already be calculated, backtracked if that will have an impact on the customer CLA and whatever they committed to, or if that will have other impacts. If there's shipping, if there's a manufacturing, if there's a raw material sourcing problem that their intelligence gathers and says that one of the raw materials 10 steps earlier in the supply chain is currently disrupted because there's a strike in a facility in X, they will then, of course, probabilistically like iterate it through the model and flag it up on this map so they can take immediate response and have this full visibility. And then also, because of this ability to now have teleoperation, they have the ability to adjust and like dial into these components from this control center and adjust these steps directly from here. So that's a really easy step to utilize all this data that you have captured and all the systems that you already put in place in the past years. The concept that I just mentioned earlier is the shift from like a line to a matrix manufacturing, where you're trying to like get capability closer and like put it essentially into a cell. So that's like a fully digitized process where each cell has a certain capability, and use automated systems to transport the goods in progress, or the work in progress to these sites. So of course, both of these examples that I have here are from automotive, because that's always the most advanced sector. But the point here is you can translate that and say, what if you're dying, or your other steps in the process can be made smaller, can be made more flexible, and you can transport work in progress goods rather than entire batches between facilities. And that might allow you to have then again smaller batch sizes, which allows higher customization, faster turnaround time, and so on, and also like get you better utilization of equipment. And so that really can be a step change. And it's like one of the big core concepts that people say is an advantage with Industry 4.0. You can upend the idea of this assembly line to have like the cell of capabilities. And then finally, one thing, and this again is really highly powered by software, is that now these processes, you shouldn't always look in isolation. You look at what is the value that they can drive. And this is like where the step change comes in. A good example is generative design, where you essentially define the constraints, then you use simulation and you figure out what the end result, the computer figures out suggestions that then the people can iterate on. And one example is in aircraft manufacturing, where they have a certain rigidity requirement on the separation for the stability of the hull, but they want to minimize the weight to minimize fuel. Of course, they put that as one of the key examples into like a generative design. You can pick it up, that software you can get today. And then it figures out that this is the best structure to minimize material, but still have the same rigidity that you need at the anchor points that you have. Similarly, you can use this algorithmic design and the ability to use all these existing systems to get limitless complexity. So complexity now comes for free, allows you personalization, higher value add with the existing facilities you have in place. And this really is taking lots and lots of steps. And this is timber construction, where you do prefab in place and you bring it to the location. But you can think of similar steps where you can do more customization, or you can maybe do more delicate shapes, more larger scale shapes that you might not have been able to do with existing processes or with new facilities by using new technologies that can make use of larger spaces. And similarly, I showed you the robots that picked up goods from a shelf before with an arm. You can use very similar systems to say, do super large scale like application and grinding, polishing, construction that previously would be limited by the length of the arm that you deploy. And you might see applications where you can use new technology with these ideas. I'll mostly skip over this, but this is like now, last year, this year, the next few years, this is the biggest trend these days, is automatic facility inspection and monitoring. And that is an alternative to putting sensors on everything. There might be things you might not be able to easily sensorize. This way, especially if you have large scale facilities, you can look at planning automated missions to monitor your plants and notice anomalies. Like, I don't know, if there's something in the way that shouldn't be there, like a pallet in a walkway, or if you have analog sensors, as like shown here, you can measure the analog sensors with algorithms, or you can take the noise level or heat on a machine. And heat can also be like, thermal cameras are really expensive. You can't put a thermal camera everywhere in your facility. If you have it on a robot that moves around, you can do it. And you can measure, for instance, if there like a machine gets too hot, that can be a sign of wear and tear that you might not be able to capture otherwise because of the price of it. And yeah, we've also seen that in really large scales with autonomous driving and parking. But one thing I might be more close on, I think this is close to where I'm going to close, is that a lot of these things are purely software based these days. And a good example is route optimization. If you think delivery services in the past, very famous in the US, the delivery never takes a left turn, in left driving countries a right turn, to optimize, to minimize stoppage and to have like less fuel use. We've also seen companies completely calculate the fuel they load onto a vehicle just based on the actual load they're loading today to reduce the fuel burn due to fuel carried. But what we're seeing now is, outside of these companies that have it for in-house use, we're seeing companies such as the routing company that I'm very familiar with, that allows you to do planning of how many vehicles do you actually need on site to achieve a certain service level, and what is the maximum capacity that you can get out of your existing equipment. And this is like really interesting when you say, I have this many forklifts, I have this many what is the maximum I can ship in this warehouse? And this is something you can simulate and you can figure out today. And one of the key questions here is, how can you take all of these existing knowledge and how can you maybe redesign your workflow routes within the facilities that, for instance, if you only selectively apply one solution, such as AGVs, which we saw one in the initiatives, that can, say, drive a lot faster than you would ever allow to drive a forklift in your facility. How can you do this? How can you bring in selectively technology, and how can you maybe just do slight operational changes based on simulation? And one way to get there are digital twins. And this is something I'll skip over because it is something you can buy as a solution. It takes very little time to like look at what minimal changes to your warehouse layout, what they can give you as bottom line impact. As quick case studies, one example I'd like to highlight is this one. This was using technology that has been around 30 years. robots that have been around, welding technology that has been around. There's no hardware innovation, no technology innovation here. All of this is software, and this was an artistic demonstrator that you can build, like you can 3D print metal to build delicate structures. But the real value there wasn't clear. They didn't really crack the value proposition. But seeing these examples help people to realize you can take these into industries where these requirements really give you value. And this is where I'd like to close on as an example. You can take off-the-shelf hardware that is readily available today that might have been super cheap because of industrial supply chains in another industry. And that allows you to combine that with software and with a key insight into the innovation and how you want to deploy it to drive a product. And this is an example, same concept, same welding technology, same industrial robot. They use this to do super large scale printing of space engines for rockets. And this is like a high value. This is like a multi-step 10x, 100x increase in value that they create, because they can now create highly complex design in very large work volumes that is previously not possible, with an investment that you see here of probably maybe 300, 400,000, which is nothing compared to the value that they can drive from a single produced piece of manufacturing, just because they recognize there is the trend that the hardware is really cheap. We can do the software today, and we can get the right sensors to get this 10, 100, 1,000x innovation. However, coming back to like the just Industry 4.0, there's lots and lots of case studies that the WF is curating together with McKinsey. You can look that up. There's 54 globally where they exactly go into the details of what technology they put where. 14 of them are like considered to be best in class, where they go all the way from the earliest part of the supply chain all the way to the very end of the customer, at the consumer at the end of the value chain. And you can look at these online. Good. Finally, to close quickly, lots of questions to take away and ponder. I've seen last week you've taken a lot of these already, but yeah, some of these, again, we had that earlier. What are the inefficiencies you see in the existing processes? What are the processes? Do map them out. Where do you have spare capacity, and what can that be used for and leverage into initiatives? We've seen fantastic examples that you presented on Friday. And then if you want to translate that to new industries, what are really the unique expertise and capabilities that you have? What else can it be used for? And that really is often where this big 10x change comes from. You might have an expertise that is absolutely standard and core to delivering your current value, but it might be completely a game changer in a different area. And then how can maybe these things that I've showed today help you in doing this process? Good. And in closing, everything of these things, they're either available today, they're available the next 3 to 5 years. And a lot of these things are open software, open hardware, or off-the-shelf hardware. You can get them. There's no barrier to getting them. And a lot of these days are moving towards self-provisioning. So you can play around with them yourself, see if they are fit for your application. And if not, you might be able, because it is now dematerialized in the level of understanding required to enter, you suddenly can have a very large talent pool to get into areas that just 5 years ago would have required really specialist skills in very, very competitive labor market. And then finally, we had the question earlier, you already have data sources, look at them that you have. And if you don't have the granularity that you think you need to deliver something, what open data sources can you use to augment your data? An example, you might have your logistics channels. You can use open data on street layouts that you don't have to pay license fees for to augment street layouts. You might be able to get government data on, like for instance, where certain facilities are, public infrastructure, that they capture as part of their service that can help you really augment what you already have to get a higher level of value out of it. And then finally, don't just deploy technology for technology's sake, and also always ask what is the easiest solution to a problem at hand. It might not have to be a machine learning or computer vision model. It might just be a very, very cheap sensor that tells you whether something is open and closed. All right, I hope these were interesting insights. Sorry for running over, and I'm very much looking forward for the questions and discussion now.
Yeah, does anyone have any questions? Meanwhile, Wolfgang, you have exposed us to a fascinating world and truly stimulated our thinking. I think it was a brilliant session, and I particularly, was impressed with the superior quality of your videos. Because typically when we see sessions, we see buffering videos and stuff, but I think it was amazing. and your generous sharing of examples and, painstaking taking time to explain is very much appreciated. Thank you on behalf of all of us. I just want to check with our sprinters if they have any questions. If not, we can wrap it up here. Does anybody have any questions? Heady stuff, huh? So if you're catching the chat, people are thanking you for an informative session, Wolfgang. I would just like one of you to come off mute and tell us how you're feeling about the session right now. Any one person, please come off mute. I think that's the least we can do. Savita, you are usually a spokesperson. I'm inviting you to come on.
Thank you, Zahira. I would
Go
say
ahead.
definitely a very wonderful and insightful session. So much so to grasp, and definitely we will with time, I guess. Maybe, we need to watch the video again and again. It's so much so. And as you said, that the quality of video is really good, because when we see such interventions, generally things are not of this good quality. So it has definitely opened, like we are, since the beginning of the sprinter, we are talking about, it is more about the growth mindset and coming out of the fixed mindset. So such kind of interventions, and the way he he has shown us the global trends, how things are happening, how things are going far beyond what we generally see on the name of Industry 4.0. So I would say that it was much beyond what I was thinking till today, what Industry 4.0 is. It is much beyond that, definitely a broader horizon and a broader perspective. And I'm sure everybody who has attended this session might be having the same feeling, that this session has actually helped us to understand in the right perspective that what Industry 4.0 actually means. So for me, it has definitely opened up many other windows, that what I was assuming till today, that what it is and what it actually means, and how fast the world is moving. It's resonate with the book that you given us at the very beginning, that the future is faster than you think. So it goes very well on line of those, that things are moving much faster on the global platform than we think about when it comes to AI or robotics or things like that. So great insight, I would say, and definitely it has helped us to learn many new things today. So thanks to the trainer.
Thank you very much, Savita. I think you really captured the essence of all that Wolfgang was trying to share with us today. Thank you very much. I would like anybody from the plant to just share his or her views. Anyone from the plant? Come on, quickly. Let's do that, and then we'll let you all go away. Any one person from the manufacturing setup? Savita, would you like to nominate somebody?
I was just going through the list to figure out if we have much people from there, but I don't know whether Abhinav is still in the operations or not, but Abhinav is there and Girish is there. So if they want to talk and if they want to express.
Yes, Girish or Abhinav, one of you please come off mute. Hello? Is anyone wanting to say anything? If not, I think it's okay. I don't want to push y'all anymore. Wolfgang, thank you. Really, I think you just changed a whole impression about Industry 4.0.
I think people are still, I'm sure people are still trying to, digest so much, so that so new things and so many wonderful things are being shared. So I'm sure that people are still in the process of digesting all this. But I'm sure everybody has liked the session very much, and maybe short of words to express, but I'm sure it has been, beneficial for everyone.
Thank you, Savita. That's very kind of you. We appreciate you giving us this feedback. And once again, Wolfgang, thank you very much. Really appreciate the time you've spent with us. Thank you. Goodbye, everybody. Bye-bye.
Goodbye. Thank you all. Thank you.
Good night. Have a good evening.